Today we're going to talk about the super exciting topic of NDK Crash Handling. I don't know what else could be more exciting, to be honest. NDK Crash Handling is hard. How many of you think otherwise? So this quote is pretty accurate. At the end of the next 30 to 40 minutes, I hope that you'll appreciate the complexity of this problem, and I hope that you'll gain a better understanding of just how native crash handlers work, what exactly they do and how they do it. This might help you if you're building your own, if you're crazy, or it'll actually help you gain confidence in using an already existing crash handler. I'll start by illustrating just how simple Java crash handling is compared to the native world. Then we'll jump into the native world. And throughout all of this, I'll talk about some of the approaches that my team and I have taken in building NDK support for Crashlytics. As many of you know, the main error handling mechanism in Java is exceptions. You can do two things with an exception. You can throw it or you can catch it. An interesting thing happens, though, when you throw an exception and you never catch it. In this case, Java invokes its default Uncaught exception handler. This thing does some processing and gracefully shuts down the Java virtual machine, the JVM. The processing that it does includes printing the stack trace to the logcat, for example, or to the console. The important key, though, is that it shuts down the process gracefully. Helpfully, there exists a mechanism for us to install our own default Uncaught exception handler. Even more helpfully is what's delivered into this default Uncaught exception handler. Spoiler alert, everything. There's an object of type throwable that has all sorts of interesting crash information, including the thing that we're after, which is the stack trace. We simply just need to call the getStackTrace method on that object, and what do we get? We get this beautiful thing. This is a very robust stack trace. It has everything that we need to pinpoint exactly where the exception was thrown. Specifically, the line number and the file name, and of course the functions, and of course all the functions that led up to the crash. As it turns out, exceptions cause a controlled JVM shutdown. This means that the JVM doesn't crash, it just exits gracefully. And this means that in the context of our Uncaught default exception handler, we can use all standard Java facilities. So we can open files, we can read them, we can write them, we can even do networking. So you can imagine having an exception handler that pings some backend to say, hey, a crash has happened. And this is great. Usually, what most Java crash handling frameworks do for Android is in this default Uncaught exception handler, they collect process information, including the stack trace, and they write it to a file. And then when the application restarts, they take that file and they send it to some backend for processing, perhaps to be displayed on the dashboard. And that's it. To sum it up, we install an Uncaught exception handler. When it's invoked, we collect interesting information about the process, including the stack trace. We write it to a file. And then when the application restarts, we read that file, send it to a backend for processing to be displayed on a dashboard. Is NDK this easy? I don't know. Well, let's find out. There are two main languages in NDK development, C and C++. C doesn't support exceptions at all. In fact, when an unexpected error occurs in C, a signal is raised. What's a signal? A signal is an operating system mechanism that informs the running process that it's violating some constraint. For example, if you try to access some piece of memory outside of your address space, the kernel will say, I don't think I'm going to let you do this. And the way it says it is by delivering a signal to the process. And the process needs to deal with that signal. C++ does support exceptions. And it does have a mechanism to install an Uncaught exception handler. In fact, you can install two of them. 100% more exception handlers than Java. When a C++ exception is caught, it behaves similarly to a Java exception. But when it's not caught, there's an interesting thing that the standard says you must do, which is in the uncaught exception handler, you have to call std abort. And std abort raises a signal. Interesting. Exceptions also don't catch the most common type of native error, which is a segmentation fault, right? You corrupt some memory accidentally. That happens to be outside of your address space. You try to access it, and you get one of these beautiful things that we all hate with a passion. So our most broad error handling strategy is just to deal with signals and forget about exceptions. This covers both C and C++. The only downside is in the case of a C++ exception, we lose the exception message string. So if we all remember, you throw an std runtime error, you can give it a string. That string, we lose it. We don't need it. We don't need it. Installing a signal handler is very easy. It's even possible to save the previously installed handler and invoke it once you're done processing the signal. This facilitates signal handler chaining. So if you have multiple NDK crash handlers installed, each will get a turn processing the signal. Even if you don't have multiple installed and you don't want this, it's still good to invoke the previously installed one, because on Android, we get a very helpful thing. The default signal handler on Android interacts with debugger D, the debugging daemon, and it prints the stack trace to logcat, which is very helpful in local development, local debugging, et cetera, et cetera. You can even install a different signal handler per signal type. So in this case, we have a sig_seg_v. This is a signal type. This is actually a macro. It's defined to some integer. But there are a number of these signal types that correspond to various categories of errors. And you can install a different handler for each one of those. The problem, though, is when our signal handler is invoked, we get almost no information. In fact, we only get 3 pieces of info. One is the signal number, so this is the sig_seg_v macro, 4 or whatever it is. We get a supplementary signal structure, and we get something called a context. We don't get this neat object like throwable that has the stack trace or any other interesting process information. We basically get nothing. And it gets worse. You thought I was going to say better, but no, it gets worse. There are a number of constraints imposed on the signal handler. The 2 most interesting ones are async safety and static storage duration concerns. Async safety means that all functions called within your signal handler need to be reentrant, because the whole signal handler needs to be reentrant. What does this mean, reentrant? Well, it means that no function can have any global side effects. So you can't take locks, and you can't reference any global variables. Why does this constraint exist? Well, imagine that the first thing that you do in your signal handler is take a lock and then go into the critical section. As it turns out, another signal can be delivered to your process. And the processing of this signal stops, and your signal handler is invoked again. And guess what? The first thing it needs to do is take that lock. Can't. It's already taken. Deadlocks. So the signal handler can be interrupted by another signal. What this constraint also means for us is that we can't use any or a lot of very useful functions from any of the standard libraries like libc and libc++. In fact, there's a small list of async safe functions that we are allowed to use, and we use those as building blocks to reinvent the wheel in an async manner. So to illustrate just how serious this is, you can't allocate memory. You can't call malloc, you can't call new. This is because malloc and new delegate to a stateful allocator that takes locks. So you have to think of other ways to get memory. One way to get around this is to use a function called mmap. Mmap returns this segment that you have to manually manage. The best strategy, though, is to not allocate any memory at all. It's kind of hard. You need memory. For similar reasons to async safety, you can't access anything in static storage duration. Static storage duration is a phrase from the standard. What it means is for the lifetime of the program. An example of something in static storage duration are function scoped static. So if you have void foo, static int I, this lives in static storage duration. A better example, though, is global variables. Global variables live in static storage duration. You can't access them. Why? Why does this constraint exist? Well, imagine your program starts up and all of the global variables start being constructed. And if we remember from our C++ days, the object's lifetime begins at the end of its constructor. Imagine you're in the middle of the constructor, a signal is delivered, the signal handler is invoked, and the signal handler references this yet unconstructed object. What happens? Yeah, undefined. No good. What this constraint means for us is that we can't pass any state into our handler. An example of some state that you might want to pass in is the file name of the file that you want to write the crash to, or a handle to the sensor manager in case you want to get the orientation of the device at crash time, which is something that may be useful to you. So I lied to you, I'm sorry. You can access one global variable, just one. It's an atomic integer, and you can't even read it, you can only write to it. Typically, you'd write a 1 to indicate that a crash has happened. The use case for this, I think, is maybe like some embedded device that lights up a little LED if your program is crashed. I don't know. But you can imagine this is a pretty limiting constraint. And in fact, if we were to write a 100% compliant and correct signal handler, we wouldn't be able to do anything useful. This is why every NDK crash handling framework violates this constraint. Technically, it's incorrect. Practically, it works. The way we violate it is we trade that atomic integer for something called an STD atomic. So we have our state. It lives in an object that's in an M-mapped and M-protected chunk of memory, guarding it from corruption from the running process. And we access it through an STD atomic. Other NDK crash handling frameworks violate this constraint by using pipes to pass data in. So these are sort of two strategies to pass state in. What facilities actually exist for us to capture useful data about the crash, including the stack trace? More bad news. None. No facilities exist. In fact, we have to manually unwind the stack trace. There's no JVM analog that keeps track of this for us. So this is where things start to get a little bit complicated. And it took us several tries to get to a solution that we were comfortable with. For our first try, we actually tried to take advantage of the unwinding libraries that ship with Android. There are two of them. There's libcorkscrew and libbacktrace. The problem, though, is that these unwinding libraries, they differ based on the API level. So for example, for Android 4, it was libcorkscrew. For Android 5, it was libbacktrace. Anything prior to 4 had nothing. The reason we wanted to take advantage of this is because our SDK would be much smaller, right? We would be using a facility that's already on the device. Additionally, anytime that those libraries update, when you receive an Android update, we would get those updates for free. This is great. But probably the most important reason we wanted to do this is because we didn't want to write an unwinding library. This is super complicated. So how did we take advantage of this? Well, we exploited linking and loading. Linking refers to the process of combining one or more object files into a single executable. An object file is the end result of a compiler, and linking is most often heard in terms of using in the context of using a library. And there are two types. There's static and dynamic. When you statically link against something, this program called the linker, it takes your binary and your library, for example, and the way it combines them together is by injecting the machine code of the library into your binary. So that when this other program called the loader tries loading your binary, it has no idea that you're using a library. In other words, your binary has no dependencies. The downside to this is a huge waste of space. It's a massive waste of space. Imagine that you have a phone with 300 apps and each one has a copy of libc. You'd need like a 1 terabyte phone to have 300 apps. No good. Also, if there was ever a patch to libc, you would have to update every one of those applications. No one got time for that. Luckily, there's a different kind of linking. It's called dynamic linking. And here, the linker merely instruments the final executable that it has a dependency on some library. So when the loader tries loading your program, it says, oh, hang on, you have a dependency? Let me load the dependency first and then continue. This reduces the size of your executable. And now, in our example of 300 apps, now they're all smaller and they share just one copy of libc, which is great. The problem, though, is that your app now has a dependency. And if the loader, when trying to load it, can't resolve the dependency, in other words, this library is missing from the device, the loader is going to return an error, and it won't be able to load your application. This is important to note because we can exploit this for good. There are times when neither static nor dynamic linking are appropriate. For example, if you want to conditionally use a set of libraries. So use library A if it exists, otherwise use library B if it exists, otherwise use library C, and so on. Neither static nor dynamic linking are appropriate for this. So what do? Well, there's a POSIX function called DLOpen. It allows us to invoke the loader programmatically. We give this function the name of the library that we want to load, and what it returns to us is a handle to that library. Coupled with another POSIX function called DLSym, it takes the handle and the name of the function that we want to execute, and it allows us to call a function in this newly loaded library. The only caveat here is that the library that you want to load needs to be set up for dynamic loading. This means that all of the symbols that this library exports need to have the C language linkage, meaning they can't be mangled. So how did we use these concepts in our initial version of Crashlytics in order to take advantage of the libraries that shipped with Android? Great question. I'm about to tell you. So Android ships with libcorkscrew and libbacktrace. Our goal was to use libbacktrace because we expect it to be available on all API levels going forward. But it's not set up to be dynamically loaded. And if we link our primary artifact, libcrashlytics SO, against libbacktrace, and it's not present on the device, we're going to crash, basically. To solve this, we ship a supplementary artifact called libcrashlytics envelope that links against libbacktrace. And then we DLOpen libcrashlytics envelope from libcrashlytics SO. If the DLOpen succeeds, we know libbacktrace is present on the device, and we can use it through the envelope. If it doesn't succeed, we fall back to libcorkscrew. Well, libcorkscrew is set up to be dynamically loaded. And if neither one is present, because we're running on some old device, we forego unwinding completely, and we only return the topmost stack frame. And we can get this stack frame from that context that we get in the signal handler. But how do we link against libbacktrace if this is a thing on the device and it's not part of the Android NDK? Well, there are two ways. You can either pull it from an emulator or an actual device, but this limits you to the number of architectures that you can emulate. Or you can build it from source, link against it, and then throw it away. This is what we did. This worked well for a while until Android N. Oh, Android N. The security policies in Android N became a lot stricter, and it prevented us from using any system libraries. Can you believe this? Why would they do this? Probably for good reasons. So we pivoted a little bit. We decided to deliver libbacktrace as part of our SDK. It became a little bit bigger, but it continued working. We had to leave the libcorkscrew mechanics in place because libbacktrace doesn't compile for ARMv5. So for those devices, we go through that schema of if libcorkscrew is present, use it, otherwise just the topmost stack frame. As more people adopted this solution, we started getting reports of reliability issues. And we started investigating this. We created just a simple app to test things out. And what we saw was that if you launched and crashed the app maybe 10 times, you'd get either 0 reports or 1 report. No good. We don't want to be that unreliable. Looking at the way our code was structured, we realized, okay, our code is async safe, nothing in static storage duration. But the allocator, the unwinding libraries are not async safe, and we were using them from our signal handler. So what do? We actually went through the exercise of replacing all calls to malloc and new in these unwinding libraries with our own async safe mmap-based allocator. Although this improved reliability marginally, wasn't where we wanted it to be. In addition, we found that sometimes the process just stopped. There was nothing in the log, and debugging it was very challenging. Attaching the debugger would make it go, or adding a simple printf or logging in any way would just make it work again. So we thought, you know, instead of trying to figure out what's wrong, let's rethink how this works. So we experimented with fork. The idea was to fork a child process, replace it with something else, attach to the crashed parent, and ptrace it. This would allow us to unwind non-main threads, and using the exec family of functions creates a new address space. So the process that we're replacing doesn't need to have async safety concerns or static storage duration concerns, et cetera, et cetera. The problem with this approach is the synchronization between the parent and the child is very tricky. As soon as you fork, you need to stop the crashed parent and wait for the child to complete its thing and then go on. Once we figured that out, once again, reliability improved marginally, but ultimately we decided to go with something else. What if you could capture the process memory now and unwind it on the back end at some other time? This would reduce the amount of work that you do in the signal handler. It's still a lot of work, but it's much less than unwinding in a crashed context. And it would reduce the need to do such silly things as replace allocators in unwinding libraries. Luckily, the most recent version of Breakpad did just that. Breakpad is a Google open source crash reporting project. It allows you to capture and process crashes. The Breakpad client captures the process memory in an async manner and writes it to this thing called a mini dump. Mini dump is just a file. It's actually the same format that Windows uses for its crash files. And this mini dump can then be sent off to some backend to be unwound and processed. So this increased our reliability by quite a lot. We were happy with this solution, so for the time being, we're sticking with it. But what do the results of this look like? This doesn't look very robust like the Java stack trace. What's going on? Well, this is an unwound stack trace, and each one of those hex numbers is actually the address of a symbol, but it's not the symbol. So we're only halfway there. And you thought this was easy. What we need to do is we need to convert these addresses to their actual symbols. This process is known as symbolication. In order to understand where these symbols come from, we need to just talk a little bit about the compiler-linker interaction. So the compiler produces these object files, and these object files have a symbol table that has a mapping of address to the symbol name. So when the linker takes these object files, it links everything into the final executable that also has a symbol table. And in this symbol table is what we're after. On Linux-like operating systems, the executables are stored in this ELF format. This is just an organization of a file. And it has several sections. Two of the sections we're interested in, symtab and dying_sym. These are the symbol tables. Each entry in one of those symbol tables looks like this and has 3 attributes that are of interest to us: the name, the value, and the size. The name is, as you guessed it, an offset into a strings table that has the actual symbol. The value is the start address, and the size is the size of the symbol. So in this example, my function starts at 2344 and is of size 48. So we take our unwound stack trace and we iterate for every one of those addresses. We see, is it between these 2 addresses? And if so, we can then say this address is attributed to that symbol. However, there's a problem. As it turns out, ELF only has exported symbols in its symbol table. No inlines, none of that. And this is a problem because it gives us a very coarse granularity. In other words, in this particular example, the crash would be attributed to my function instead of generate, which is where we want it to be attributed to. It's not very robust. And if you have well-factored code, well-written code with a lot of optimizations, a lot of things get inlined. So what do we do to fix this? Well, there's this other thing called DWARF. It sits alongside ELF. And initially, DWARF was just a play on the name ELF, like elves and dwarves. But now it stands for something else, debugging with attributed record format. And this thing describes the structure of the program in very high detail. In fact, the DWARF sections of the file sometimes are huge. That's why they're only present, most of the time, they're only present in the debugging builds. Similar to ELF, there are sections. The section that is of interest to us is the debug info section. A debug info section is a flattened tree of the structure of the program. So it describes things like this function calls this function was inlined here, it went through this namespace, here are some variables, here are some template arguments, et cetera, et cetera. But using this data gives us enough granularity to symbolicate the stack trace properly. So in this example, we see that there's an attribute that's the name. So this is the symbol. It's actually also an offset into a strings table. And then there's this thing called the high PC and the low PC. So it's similar, very similar to ELF. Instead of the start address and the size, there's the start and the end. So we can use the same sort of scheme and probe each one of those addresses in our unwound stack trace to see if it's within the bounds of high and low. And if so, we attribute it to this symbol. But what about this entry? Man, just when you thought things were getting easier. This entry has no name, it has no high PC, no low PC. What's going on? Well, the key here is this abstract origin. This is a pointer to another entry. And if we follow that pointer, we get to yet another entry. And we follow that pointer, we get to another entry. Luckily, there are no more pointers. And when you look at this holistically, you finally have enough information to symbolicate your stack trace. You have the name, and you have something called ranges. Now, in the previous example, there was a high PC and a low PC. Why is there ranges? Well, it turns out that a function can span non-contiguous memory. This can happen in various inlining scenarios, probably with templates. But this ranges entry is an offset into a ranges table that is a list of high-low pairs. And so we just need to do a little bit more work to probe each one of those addresses, probe this data for each one of those addresses in our unwound stack trace to see what symbol it belongs to. So now, thanks to DWARF, we're correctly attributing that same address to the correct function, which is generate. But how do we collect all of this symbol information, and how does it relate to the crash? Well, for us, in Crashlytics, we have a Gradle plugin that hooks into the build process. So anytime you build, it will read your debug binaries, collect them to a file, and send it to a backend for some processing. And it's processed in tandem with all of your incoming crashes. Finally, we get something that's usable to us, specifically this part. This has function names instead of those funky addresses. So this is a fully unwound and symbolicated stack trace. You notice that it's missing file and line numbers. There's another section in DWARF called debug lines that we can probe for that information as well. But I think we're out of time. So hopefully you now have a somewhat deeper understanding of how these native crash handlers work. Specifically, you need to safely capture a crash. You need to unwind it. You need to symbolicate it. And the most important part is you need to provide a seamless experience to do all of this. You can't have the developer doing these 20 steps every time they build just to get a native crash report. With this information, like I said, you can build your own, or you can use an already existing solution like Crashlytics. Thank you.